Jieming Wang from Tianjin University. Today I will introduce the validation and improvement of the hybrid central solver for high-speed and multiphase flow. Then I will go over the following aspects. As you can see in this picture, the global carbon dioxide emissions are increasing dramatically in recent years. And by sector, the transport accounts for about 21.5% of global carbon dioxide emissions. So it is significant for the reduction of carbon emissions in transportation. To achieve this goal, we can use alternative fuels. Here are some common alternative fuels. The gas fuels represented by hydrogen and methane, usually injected into the engine directly for high volumetric efficiency, and also for sufficient in-cylinder mixing. The high injection pressure is usually required, and this high pressure may cause the high-speed flow in the internal combustion engine. So there is a big probability of mark discs near the nozzle. And other alternative fuels represented by ammonia and methanol has poor ignition performance. So it often requires high ignition energy. So active pre-chamber system can be used for the reliable ignition of these fuels. And also the flexible and controllable combustion process can be accomplished with spray injection in the cylinder, and under actual engine conditions, the pressure and temperature inside the pre-chamber rise, and there is a big probability of mark discs when the gas passes through the nozzle into the cylinder. So the usage of alternative fuels and new combustion technologies can make the flow field in internal combustion engines increasingly complex. So it requires simulation tools that can not only steadily solve the low-speed flow field and simulate the local supersonic flow field simultaneously, but also deal with pre-combustion problems. In official OpenFOAM solvers, the raw PeopleFOAM uses people algorithm, but this algorithm may get numerical oscillations in the regions of flow properties discontinuities. So this solver is mainly used for low-speed flow. And another OpenFOAM solver called raw central foam uses explicit KT-KNP scheme. This solver can capture the discontinuities in high-speed flow very well, but the timestamp of this solver is strictly limited by set field number. So in the case of low velocity flows, the timestamp of this solver is very small. So this solver is mainly used for high-speed flow. Both of them do not meet the requirements. OpenFOAM third-party solver reacting people-centered foam developed by Combustion solved this problem by combining the people algorithm with the KT-KNP scheme. This solver can steadily solve the flow field with Mach number range from 0 to 5, and the original raw central foam uses explicit KT-KNP scheme. So it is computational inefficient in low-speed flows with Mach number below 0.3. To solve this problem, in this solver, the KT-KNP convective fluxes are formulated from the unknown fields from the new time layer, yielding to the implicit approximation of a convection diffusion equation. And the pressure, velocity, and energy equations are coupled with people algorithm. In addition, the convective formulation for compressible flow differs from that for incompressible flow. So a factor related to the velocity of the flow field is introduced in this solver. When the velocity of the flow field is high, this factor tends to 1. So there is positive convective flux phi PF and negative convective flux phi NF in the flow field. When the velocity of the flow field is low, the factor tends to 0. So there is only one convective flux in the flow field. This factor makes the convection formulation suitable for a wide range of flows. Then I will show some validation cases of the solver. The first case is from NASA official website. This is a subsonic jet with Mach number about 0.5 at the jet exit, and the nozzle surface was set to a diabatic solid wall, and other boundary conditions were set to free stream inflow conditions and outlet conditions. And the two-dimensional mesh fields can be downloaded from the NASA website. The key omega SST model was used as the turbulent model, and the data of the velocity was extracted along the y-axis, the lines of x equal to diameter of the jet, x equal to 5 diameter of the jet, and x equal to 15 diameter of the jet. And the original data was normalized by the value of velocity at the jet exit. And then we can get the following figures. The two figures show that the two solvers performed very similar, and the results were in good agreement with the experimental data. But there is a little difference. It may be because the model, it may be because the grid is a little coarse. And this two-dimensional figure about the velocity distribution visually shows the similarity of the results of the two solvers. And the next case is also from the NASA database. It has the same model and boundary conditions with the last case. The only difference is that the pressure of the inlet flow is a little larger. So the Mach number at the jet exit is approximately to 1. And the key omega SST model is also used. The pictures also shows a good similarity of the two solvers. And the little difference between the results and the experimental data may also be caused the mesh fields. And also, this two-dimensional figure also shows the similarity of the two solvers. The third case is a transitional supersonic flow over a backward-facing step. This case is from ANSYS Fluid Dynamics Verification Manual. The Mach number of the flow is about 2.5, and more details about this case can be found in this chart. There are 48,128 cells of this two-dimensional mesh, and K omega SST model is also used. And the data of the pressure was extracted along the sample line on the bottom surface, and the original data was normalized by the static pressure at the inlet. We can see in this picture that Rho centrifugal and the reacting pimple centrifugal, both of them have good agreement with experimental data. And the reacting pimple centrifugal performed better at the first half of the sample line. These pictures shows the lambda shock wave calculated by the two solvers. Their results are very similar. To solve the spray combustion process in the internal combustion engine, we need to improve this single-phase solver. The Lagrangian libraries were added into this solver for particle tracking, and dynamic mesh libraries were added into this solver for adaptive mesh refinement. And here are all of the changes at the new solver. First, the libraries should be added into the options file, and then the new codes about the new libraries should be added into the C file, and then the equation fields should also be modified for the new libraries. And the new solvers was validated by Acombaum in the OpenFOAM tutorials. This case is about the combustion of an unhaptened spray. The penetration distance of the two solvers were compared, and as you can see in this picture, the new solver gets a larger result, and these results were from the cases with static mesh. The dynamic mesh was also accomplished in the solver. The following pictures shows the refined mesh at 0.6 milliseconds based on the K field. And other fields can also be selected for the practical demands in the safety simulation. Here are the conclusions. First, with the usage of alternative fuels and new combustion technologies, the flow field in combustion engines will be complex, and reacting PMO syndrome can solve this problem. And then we validate this solver by 3 flow cases: subsonic, near-sonic, and supersonic. And then for spray combustion, we add the Lagrangian libraries and dynamic mesh libraries into this solver, and it also shows the good extensibility of this solver. In terms of flow, this paper demonstrates the potential of this hybrid algorithm for safety simulation of advanced internal combustion engines. Thank you for your attention.
Okay, thank you, Ms. Wang. It's a very good presentation. So we have time for 2 questions. Is there any? Okay, I have a small question. I think it's on page 3. You are using a planning factor to switch between the pressure solver and the density solver. So why did you divide it by the Seifert number, Coulomb number? In calculating the Mach F, you divided by calculating the Kf, you divided the Mach F with the Coulomb's number. Why did you do that?
Sorry, I beg your pardon.
就是你为什么除以那个布朗的数？你的那个马赫数为什么要除以那个布朗的数呢？
哦。
那个计算 Kf 的时候。
Oh, this is just this is just a definition of a new factor. This is a new factor.
Is it a constant value?
Yes. No. The Mach number is not constant. This is not a constant value because the Mach number